This video is going to introduce the concept of current, electric current. Up until now we've been dealing with electrostatics, so that for the most part the charges were not moving around on us. Maybe we would have one electron or proton at a time that was moving through an otherwise static electric field, but now we're going to talk about a situation where the electric charges, lots of them, are all moving usually together in one direction, and that idea is called current. Of course, the primary application of this will be circuits, electronics, right? All electronics involve a circuit in which electrical carriers, things that hold an electric charge, are moving around basically in a big loop, in a big circle, and that is what causes the device to work. So we're getting very close to very practical applications, and although that we're not going to delve completely into the full, this isn't an electronics course and we're not going to delve into everything we could talk about in terms of circuitry, we'll just touch on it and we'll just talk about the basics. So here's the official definition. Current. Current is the rate at which charges move through an area. So let me draw a picture. Let's say we have, and I mean we might as well start thinking of it as like a wire. Let's say we have a wire, and of course if it's made out of metal then it's a conductor, and so there are these free electrons, and when the conditions are right, these electrons will be moving through the wire. We'll talk about that more in a little bit, but let's just assume they're already moving. So what we want to do is imagine a particular spot in this wire, and now imagine all these electrons, negatively charged things, okay, and they're all moving. Let's say they're moving to the right. So you can imagine that after 1 second has elapsed, a certain number of these electrons will have passed this little barrier that we've created in our minds, just this little line in the sand. So a certain number of coulombs, a certain amount of charge, will have gone through this spot in the wire. And that's what current is. It's how much charge goes past any given point per second. So that's the rate part of this. It's a time rate of movement. Okay, so the symbol for current is capital I, actually. So I is actually the rate of change of the charge. So it's an amount of charge per second. So it's technically the derivative of charge over time. Now we can also talk about the average current, which would be an actual some amount of charge, a delta Q, divided by some amount of time. So either one of these. This is the official instantaneous definition of current. This is the sort of over a period of time, what is the average current. So that's your official definition. Now in most cases we won't have, there won't be any difference between these two, because there'll be sort of it'll be a constant current in a lot of our applications. Okay. Now, what are examples of when charges would move? Well, electrostatic discharge. For example, when a shock happens, when you've got some static electric buildup on you and then you touch something metal, and we talked about this in class. If the electric field is strong enough, if you get close enough to the metal, the electrons are going to jump out into the air, right, and cross over. And so for a brief second, charge is flowing from one side to the other. Right? And so a shock, an electrostatic discharge. And so we can talk about the current in that situation. TV screens work with an electron beam. That's how they display a show. And so there's beams of electrons being shot onto the screen, and electrons, of course, are charges, and so you can talk about the current there. And then finally, of course, the most important one is any electronic device involves a circuit, and when that circuit has a power source in it, like a battery, we're going to have charges flowing around the circuit, and we would always want to know what the current is in that situation. What are the units for current? Well, we said it's charge per time, so we're talking about coulombs per second, and that gets its own name. Coulomb per second is called, well, the symbol is A, and that is an amp. Actually, it's an ampere officially, but a lot of times people will shorten that to an amp. This is named after a French scientist, André Marie Ampère. So that's a French last name, and he's early 1800s, one of the first scientists to study electrodynamics, the study of the moving electric charges. So he gets his name on the major unit that we're talking about. So let's do a little problem. Let's say we have a 1 amp current. How many electrons are passing a given point every second? Okay, so just so we get it's an example, but it's just so we have a sense of what an ampere is. Well, 1 amp, right? It's really coulombs per second, so this is 1 coulomb per second. But what's a coulomb in terms of electrons? Well, 1 electron is 1.60 times 10 to the minus 19 coulombs. So coulombs will cancel and we'll get electrons per second. And so it's 1 divided by 1.60 times 10 to the minus 19. That turns out to be 6.25 times 10 to the 18 electrons per second. So that gives you a sense of what 1 amp means. Very, very, very large number of electrons passing through any given point per second. I need to say something about the direction of the current. So the way we're doing it, we're not defining current to be a vector, but it does kind of have a direction. The thing is that most, for all applications we'll be doing, like in a wire, the current can be flowing in one of 2 directions, right? Like, one way or the opposite way, because it's sort of a one-dimensional situation, right? So either the current can be going this way or this way. So since there's only 2 directions most of the time, we can handle the direction with a plus or a minus. And here we have to lay a little bit of blame, although it wasn't his fault, on Benjamin Franklin's doorstep, because remember, he, not knowing about electrons yet, had to choose between the 2 kinds of charge, which one would be positive and which one would be negative. So he picked electrons, he picked the negative type of charge to be the electrons. So even though most of the time, and certainly in any circuit, in any wire, it's the electrons that are actually the things that are moving, right? So if we have electrons, let's say they're moving this way, that means negative charge is going to the left. So we would actually say the current would be going this way, because we want the current to be the direction of positive charge flow. It's usually not a big deal, but it takes a little bit of getting used to. So we're going to define, if it's electrons that are moving, the current will actually be going the other way. It turns out that negative charge moving to the left is totally equivalent to positive charge moving to the right. Even though technically it's negative charge moving to the left, we're still going to say that the current is to the right. We're going to pretend like it's positive charge things moving to the right. Now, if we ever do have positive charges moving in a certain direction, then that would be the same direction as the current. But when it's negatively charged things, which it usually is, like electrons, then the current will actually be the opposite way that the electrons are moving. Again, I apologize for this, and we're just stuck with this sort of incorrect decision back before we really knew what was going on, the choice between positive and negative charge, and we're just stuck with it. Briefly, I want to mention current density. We're not going to be doing too much with it, But current density is current per area. Okay, it gets the letter J, and it's just your current divided by the area. You can see that this will be in amperes per square meter. The A here is the unit for current. The A here is area. So yeah, so this is the unit of current density. So the idea is, if we think of a wire again, and let's say current is going this way, which, as we were just mentioning, really means electrons are moving the other way. But again, let's ignore that. Think of positive charge going to the right. Obviously, the thicker the wire, right, the more area, you can get more current sort of fit in there, and that's mostly what we want. Like the I is usually what we want, but sometimes we would want to know how much is it per square meter. Right? In other words, like how much of that current is just because it's a thick wire, and how much of it is because the electrons are actually moving, relatively speaking, fast. So J sort of divides out by the area. Okay, so like I said, we won't do too much with it, but if we ever need to compute it, it's very easy to compute, just I divided by A. Now, I want to get into maybe the most surprising thing about this. Hopefully you'll be surprised and find it kind of interesting. What are the moving charge carriers actually doing? The pictures I've been drawing so far have actually not been very correct, to be honest. I've been drawing these pictures a couple of times now where I've had electrons, and I've said they're moving this way, say to the right this time. And now, so, when I draw a picture like that, of course, you're picturing these little electrons. They're all just moving kind of in a straight line this way, to the right. But that's not really what's going on. Let me just for a second say what is really, really going on if you could actually see these electrons. Okay, so the electrons are mostly moving just in random directions. Now let's say we have a hunk of metal and it has free electrons, but let's say there's no overall current. It's not hooked up to a power source. So the free electrons, what are they doing? Well, they would just be bouncing around, really. A typical electron would just be, moving around, sort of randomly hitting other atoms, right? And just, going until it hits an atom, boom, it bounces off, hits another atom, boom, bounces off. And it'll just be going like this. And how much of that it's doing is actually based on temperature. We can think back to our chapters on temperature and on thermal internal energy, right? And we pictured atoms, just kind of atoms in a gas moving around randomly, and more so if the gas was warmer, right? Or same with a liquid. Well, in a conductor, the electrons kind of do the same thing. That's internal energy. So the warmer, the hotter, your conductor is, your metal is. The atoms themselves may be vibrating in place. That's their contribution to the internal energy. But the free electrons are kind of like gas molecules. They're just bouncing around all over the place, and they're hitting these the atoms themselves. They're hitting the nuclei of the atoms and bouncing off, and you just get this kind of crazy motion. And they're going very fast when they're doing this at sort of typical temperatures, say at room temperature, for example, going very fast. Maybe an appreciable fraction of the speed of light, for example. Okay, so they're just bouncing around. And again, this is the case when there's no current. Now suppose there is current. And this is the surprising part. Our electron, still for the most part, most of its motion is just random, very fast bouncing around, hitting, atom after atom, just going like this. But when we say there's current, what that means is that these electrons have a overall slight, very, very slight drift in one direction. So you see, like, it's still random motion. Sometimes it's going right, sometimes it's going left, up, down, diagonal, but there's sort of an overall movement to the right in this case. That's what current really looks like. That's what all these electrons are doing in a wire when they move. It's not like this nice clean picture where they're all sort of moving in a very orderly fashion in one direction. Mostly they're just bouncing off atoms in all kinds of crazy directions, but they just have a general overall push in one direction because of some external electric field / potential field that's pushing them this way. So that even after they bounce off, they hit an atom and they want to go this way. Well, but if there's some electric field pushing them, they might curve a little bit more to this way. And then they might bounce off that and come back this way and bounce off this way. And there's going to be an overall push toward the right if there's an electric field. So that's really what's going on. So the velocity of charge carriers is very complicated, as you can see.